So, welcome to this class on discrete log problem. So, as we were discussing about public key cryptography, we will continue with that and discuss about the following topics. So, first we will introduce the problem of discrete logarithm problem and try to understand like what is the problem statement. We shall follow it up with an application of the discrete logarithm problem to a cryptosystem which is commonly referred to as the ElGamal cryptographic algorithm. And then we shall discuss about some popular cryptanalytic techniques for discrete logarithms, and which are commonly with the names of which those algorithms are the Shank's algorithm, the Pohlig-Hellman algorithm, and the index calculus algorithm. And we shall conclude with another application of the discrete logarithm problem to key agreement or key exchange problems, and it is commonly referred to as the Diffie-Hellman problem. So, it is a slight variation of the discrete logarithm problem, but we shall see the first of all the corresponding problem and also its application in key exchange when two parties would like to exchange information to arrive at a common key. So, first of all, what is the problem of discrete logarithm? So, consider a finite mathematical group where G is the group and dot is the corresponding operator, that is, this is a multiplication operation. And now for any element alpha which belongs to this group G and has order n. So, we know what is meant by order. So, means that if I take alpha and if I multiply it n times, then I get the unity of this group. So, let the corresponding set be referred to as this, and it is obtained by raising alpha to its various powers. The possible powers or which is referred as I can range from the range of it lies between 0 to n minus 1, both the intervals included, right. So, we know that alpha power n is not included because alpha power n is back to 1, that is it is the circular group, right. So, the discrete logarithmic problem, that is the DLP as it is commonly known as, is to find the unique integer I where I lies between 0 and n minus 1 such that this particular condition is satisfied. So, that means there are two given elements alpha and beta. The question is to find this I such that alpha power of I is equal to beta. So, basically what we are trying to find out is logarithm of beta with respect to alpha. So, this is commonly referred to as the discrete log of beta with reference to or with respect to the value alpha. Okay. So, now for proper choices of this group, like if I choose the parameters properly, as we will see in context to the cryptanalysis, that then the computation of this particular value is considered to be a computationally difficult problem. Okay. So, therefore, this is a possible or a candidate one-way function. As we have seen that in context to public key algorithms previously, like when we studied about RSA, then we have also seen that one-way functions or candidate one-way functions are important to the development of public key ciphers. Similarly, here this is also another possible candidate one-way function which can have potential applications in public key cryptography. So, discrete logarithmic problem, as we know, is the inverse of the exponentiation operation. So, if I consider the exponentiation operation in the modulo p field, then the discrete logarithm is nothing but the corresponding inverse, right. Now, exponentiation is easy to compute. We know that there is a polynomial time algorithm commonly referred to as the square and multiply algorithm, through which we can compute the exponentiation quite easily, right. However, if the group is properly chosen, then the computation of discrete log is believed to be a difficult problem. Okay. So, therefore, the exponentiation is a possible one-way problem because the forward direction is considered to be is quite easy. We have a polynomial time solution for computing the exponentiation, and however, the inverse, that is computing the discrete log, is considered to be a computationally intractable or a difficult problem. Okay. And therefore, this has got potential applications in public key ciphers. Okay. So, let us see one such application, and it is commonly referred to as the ElGamal cryptosystem. Now, you note that in ElGamal cryptosystem we will define or we will denote this p to be a prime number and consider the group ZP star. So, we know, remember what is meant by ZP star, that is here it is a multiplicative group, that is 0 is being excluded from this group. Okay. So, we are assuming that that in this prime group, that is ZP star, Okay, their computation of the discrete log problem is computationally difficult. So that is our basic assumption. Using this assumption, we will see one proposal of a possible crypto system. So let alpha, which belongs to ZP star, be a primitive element. Primitive element, we know that if I take this primitive element and if I keep on multiplying, then I generate all the elements in the group. Okay. So therefore, using this particular primitive element, what we will do is we will see how the crypto system is defined. Okay. So immediately you know that for any crypto system it is a 5 tuple, right. So therefore, there is a corresponding plain text and also a corresponding ciphertext space, right. So here the plain text is also chosen from the ZP star, that is, it is any element in ZP star. However, the ciphertext is actually a cross product of two, or it is an ordered pair, that is, you can refer to as say y1 comma y2, where y1 is an element of ZP star and y2 is also an element of ZP star. Okay. So therefore, the space of ciphertext is obtained by the Cartesian product of ZP star and ZP star. Okay. So now, what is the key of this algorithm? The key of this algorithm is the public parameter p, which is known to everybody, that is, not only the sender and the receiver knows, but also the adversary knows. Okay. Similarly, the alpha and beta are also publicly known values. Okay. But A is actually a secret. Okay. So if I just consider like a public key cipher, then P, alpha and beta is what is the public key, but A is the gives the corresponding private key, is a corresponding secret element. Okay. Now these values like alpha and beta satisfy a particular relation, that is, if I take alpha and raise it to the power of A, then I obtain beta, of course in the modulo P field. Okay. But here you note that based upon this assumption, even if I give to an adversary alpha and beta, because of the proper choice of P, computation of A is believed to be difficult, right. Now we will try to apply this particular assumption to encrypt a possible message, say X. Okay. So the idea is quite simple. The idea is when you are trying to encrypt X, what you do is that you choose a random number R which belongs to ZP minus 1. Okay. So ZP minus 1 means it will lie from 0 and continue till P minus 2. Okay. So we choose an R which belongs to ZP minus 1, and using that we will encrypt the value of X. Okay. So R is, remember that R is a random choice. Okay. So what we do is that we take X and we also pair it with a random component called R and obtain the ciphertext y1 and y2. So from this statement itself you know that the computation of y1 and y2 actually not only depends upon the plain text X, but also depends upon the random choice R. So which means that it is not necessary that the same value of X will always get mapped to the same ciphertext. So this algorithm is by definition a randomized algorithm, right. So what we do is, this is essentially computation of these y1 and y2 as two pairs. Okay. So note first of all y2 actually. Okay. So y2, what we do is this, that is, we take beta, which is essentially this value, and raise it to the power of R and multiply it with X. Okay. So that is somewhat some sort of a multiplicative masking. Okay. You take X and you mask it by multiplying it with beta power of R. Okay. So therefore what you do is this, that is, you compute y2, and remember that y2 is nothing but X, and you multiply it with beta power of R and do a modulo P. Okay. So next what you do is that you compute y1, and y1 is nothing but alpha and raised again to power of R. Okay. And again again of course the modulo P is of course there. Now you note that by our previous assumption of choice of beta and alpha, we know that beta is nothing but alpha power of A mod P. Okay. So what the receiver does is that when it receives this y2, in order to find out this value of X, it needs the inverse of beta power of R. So that means it needs to compute the value of beta power of R. But remember that the receiver also has got this alpha power of R, right. So what the receiver does is that receiver takes alpha power of r, that is basically y1, and raises both of them to the power of a. Okay. So, if you do that, that is equal to alpha power of a whole power of r, right, and that is nothing but beta power of r, right. So, therefore, because the corresponding receiver has a knowledge of this value of a, computation of beta power of r is quite trivial. He can do it in polynomial steps, right. So, then what the receiver does is that the receiver computes the inverse of beta power of r, that is beta power of r inverse, and you know that by extended Euclidean algorithm you can actually compute the inverse also in polynomial number of steps, in poly steps, right. So, then what it does is that it masks this inverse or multiplies this inverse with y2, okay, and therefore, if you multiply x beta power of r with the inverse of beta power of r, then you again get back x, right. So, therefore, the receiver is able to correctly obtain back the value of x, right. But however, it is believed that if the adversary has to find out the value of x, it needs either to guess the value of a or it needs to obtain the value of a through some means, which means that the adversary should have the potential power of solving the discrete log problem in the field, okay, and that is believed to be a difficult problem, right. So, it is a quite simple algorithm that way, and now we can see the steps like y1 is equal to alpha power of r mod p, y2 is equal to x beta power of r mod p, that is the encryption step. For decryption, what you do is that you take y2, multiply it with by raising y1 power of a, you know y1 power of a is nothing but beta power of r, you compute the inverse of beta power of r, multiply it with x into beta power of r and obtain back x. So, the encryption, if you do the proper decryption in this way, you get back the original plain text x, right. So, therefore, the working of the algorithm can be summarized again like this: plain text x is masked by multiplying with by beta power of r yielding y2. The value of alpha power of r is also transmitted as a part of the ciphertext. Bob, who has the secret a, can compute beta power of r by raising alpha power of r to a, and then he obtains x by dividing y2 with beta power of r. Dividing means multiplying by the inverse. So, note that the ElGamal algorithm, as I told you, is a randomized algorithm, that is the ciphertext depends on both the plain text x and the random value r chosen by Alice, which is the encryptor, and therefore, the same plain text can actually be mapped into p minus 1 ciphertexts depending upon the choice of r, right, because you can have how many choices of r from 0 to p minus 2, that is p minus 1 choices. For each of these choices, the same plain text will get mapped into p minus 1 different ciphertexts. Okay. So, that way this algorithm is quite good because it is inherently it is a randomized algorithm, right, and therefore, it gives to maybe to nice properties which can which we require because of the requirements of semantic security. So, we will just consider a very simple example here, like for example, p equal to 2579 is a prime number and alpha is equal to 2 is a primitive element of zp star. Consider that there is a secret value 765 which is the secret component, and we just choose two values like beta and alpha. So, alpha is 2, so we just take 2 and raise it to this secret value, obtain back beta. So, note that 949 is the value of beta, therefore, alpha that is 2 and beta that is 949 are the public parameters, right, but a, which is the 765, is the secret component. So, now suppose Alice wishes to send x equal to 1299 to Bob. So, what she does is that she randomly chooses a value r equal to 853, and what she does is first obtain y1, that is by raising this 2, that is alpha, to the secret value 853, obtain back 435, and y2 is multiplying or masking 1299, which is the message which she wants to send, by the corresponding value of beta power of r. So, beta is 949 here, it is raised to 853, which is the random component, and obtain back 2396. Okay. So, therefore, when the ciphertext will correspond to 435 paired with 2396. Okay. So, if you want to, so Alice sends this one as the ciphertext, and what Bob does is that Bob computes 23 multiplied by x by multiplying 2396 by taking 435 and raising it to the power of 765, which is the corresponding value of the secret. So, you note that again that Bob has this secret value, so he can easily do this operation, but the adversary should be unable because it neither has the knowledge of this nor it cannot extract out this knowledge because of the assumption of the discrete log problem, and multiplies with what Bob does is Bob multiplies with the inverse with 2396 and obtains max x, which is 1299, which is the same as the initial value of x. Okay, that is the message. So therefore we see that mathematically if you use the ElGamal encryption, then you get back whatever message you want to encrypt with. Okay. However, we will now consider the cryptanalysis problems of the discrete log challenge. Okay, like if I want to give two values, if I am given with two values of alpha and beta, how really difficult it is to compute the value of a, and we will consider some classical examples to this direction. Okay, but before I go into that, there is a small note that I would like to make, that is, if alpha power of I. So we know that in normal integers computing logarithm is not very difficult, because when you are not considering the modulo field, that is when you are not doing the modulo operation, then your alpha power I is always a monotonically non-decreasing value, which means that if I increase the value of I, then alpha power I will not decrease, right, when you are not doing the congruence or when you are not doing the modulo operation. Okay. So which means that this gives you the scope of applying a binary search kind of technique to arrive at the value of I, right. For example, you check with a large value of I, if you see the alpha power of I, that is the value that is the beta, which is, so what you do is that you choose a large value of I, guess a large value of I, and then if you see that the beta is larger than that, beta which is equal to alpha power of I is larger than that, then you apply binary search to the larger part, right. And then if you see that it is lesser than that, other than that, then what you do is that you apply binary search to the lower region, right. That way you can actually try to converge at the actual value of I, if alpha power of I was a monotonically non-decreasing series, that is if I increase I, alpha power of I does not decrease. But the problem with this modular field is that alpha power of I mean there is no ordering of this alpha power of I. It may happen that even if you increase the value of I, alpha power of I becomes smaller, right. So therefore the only way of doing it is by an exhaustive search, that is the assumption. Okay, that is the, I mean at least you cannot engage a simple binary search kind of technique to arrive at the value of I. Therefore one possible solution is to do an exhaustive search in the worst case, right, because you may not be lucky, so you may need to verify all the values of I and check whether alpha power of I matches with the given value of beta, right. So this will actually engage order of n time, because n is the group order, so order of n times, and the storage that you require is order of 1, because you can, I am not doing any storage at this point. Okay. However, you can actually engage a time memory trade off here, okay, and using the time memory trade off you can try to reduce the value of the time complexity, however the space complexity will automatically increase, okay, and therefore you can actually do some amount of pre-computations, okay. And now what is the idea of doing that is like this. Suppose you store all the possible values of alpha power of I modulo p as ordered pairs. So what you can do is that you can store them as ordered pairs like I paired with alpha power of I modulo p, okay, and sort the elements with respect to the second parameter, that is with respect to this alpha power of I modulo p, you can sort them, right. You can immediately, because of the previous description or other discussion, you know that even if I increase I, alpha power of I mod p is not automatically sorted, right. So what we need to do is maybe engage an efficient sorting algorithm to sort this, okay. So alpha power of I, so we basically sort this ordered pair list based on the second argument. Next what we do is that we that is we search for the given challenge by employing a binary search, that is for example, so what I do is this, that is I take I and compute alpha power of I modulo p. So this is basically a pre-computation that I am doing, and what I am doing is essentially sorting them based on the second argument, okay, and I make a list, say that list is L1. So now I know that I have to look for the case where beta is equal to alpha power of I modulo p, right. So that means that if this, so this is a pre-computation stage, okay. So I have already done this and this is stored in the memory. Now what I do is that I take this value of beta and I search for, after I have sorted out, after I have sorted this list, that is, it is as it is called here as L1, which is the sorted list based on the second argument, okay, based on alpha power of I mod p, okay. So then what I do is that I take this value of beta and I search in this list using a binary search kind of technique, right. So basically what I do is that I look for its location by applying a binary search kind of method, okay. So now what is the complexity here? We know immediately that the storage complexity here will be, because of I need to store the entire list, the storage complexity will be order of p, okay. So or order of p, order of n, whatever, okay. So the storage complexity will be order of p, right. Now what about your sorting algorithm? Your sorting algorithm will have a complexity of, so I am referring to p as n, then it becomes n actually, and this is order of n log n, right. So that is your sorting complexity. Now I am also doing a binary search, so the search will actually require an order of log n complexity, right. Now but you note one thing, that because we are actually considering very large fields, their logarithm of n is actually very small or negligible compared to n. Remember that you are dealing with, say, the 1048 bit of large numbers, okay. So in that case, in such kind of big scenarios, okay, so when you are dealing with say 2048 or 10248 bit primes, right, then it may happen that this logarithm of n is actually very small, it is actually the logarithm of n is very small compared to this value of n, okay. So then you can actually approximate this as order of n and approximate this as order of 1. So when you are considering these discrete log cryptanalysis problems, we will always do this, that is, neglect this value of logarithm n compared to this value of n, okay. So therefore in this case your time complexity, okay, that is the time complexity to search is actually a constant time, okay, it is order of 1, okay. However, your memory complexity is order of n. So you see that this is just the opposite of what we saw at the beginning, right. At the beginning what we started with the time complexity of order of n and space complexity of order of 1, but using some pre-computation you can actually reduce drastically your time complexity, but of course at the cost of your space complexity. Now there is an algorithm which is called as the baby step giant step algorithm, which actually tries to optimize both, okay. So it is called the Shank's baby step giant step algorithm, and we will next see the description of this algorithm. So consider this algorithm, that is, what it does is that the problem is again the same, that is, given alpha and beta and given a choice of group and a value of n, my objective is to find the corresponding value of a for which beta matches with alpha power of a in this group, right. So what is done is like this. So first you actually set a value or variable m to the square root of n, okay, and then you start computing alpha power of mj, where j runs from 0 to m minus 1, okay. So that is, your value of alpha power of mj is what is computed and stored, okay. So that means immediately you understand that what is the amount of storage required for this, it is equal to m, because you need to do m such computations, and m is square root of n, right. The other thing which you do, and so what you do is again store this or m ordered pairs like j comma alpha mj with respect to their second coordinate, that is, you sort them by again an efficient sorting algorithm and obtain the list which is called L1, okay. So basically the list L1 is, so m is equal to square root of n, okay, that is, it is set to square root of n, and what we do is that we make a list L1 which is the sorted list based on the second argument in your j comma alpha mj. Okay. So, where your j is actually running from 0 to m minus 1. Okay. So, you compute various values of j and you find out or calculate the value of alpha power of mj, that is your list L1. The list L2 is actually made out of a different way. It's what you do is that this sorted list based on the second argument of or in I comma beta by alpha power of I. So, here also your I ranges from 0 to m minus 1. Okay. So, now you note that in L1 the elements are computed how? The elements are looking like, say, when you start with the value of j equal to 0, it is alpha power of 0. So, that is 1, right. Next you have got alpha, when value of j is equal to 1, it is alpha power of m, then alpha power of 2m and so on, right. So, it is a kind of a big jump. You see that it is alpha power of m, alpha power of 2m and so on, right. M is a quite big number, but here you are actually computing like beta power of alpha power of I. So, that is alpha power of 0, which means it is beta. Next you divide this beta by alpha power of 1, next you divide it by beta power of alpha square and so on. So, these are actually small jumps, right, and therefore, these jumps are referred to as the giant steps and these are actually the baby steps. Okay. Now, what you do is that in this list L1 and L2, which are both sorted, you are trying to find out a common element based on the second argument. Okay. So, the second argument in this list L1 is alpha power of mj, right. In the second argument here is beta power of alpha I. So, now since both of them are sorted, you can actually traverse down both the lists in linear time and you can find out an element which actually matches in the second component, right. So, that means in linear time you can find out that alpha power of mj is equal to beta power of alpha I, and you can find out the corresponding values of I and j. Okay. So, this means that beta is equal to alpha power of mj plus I. So, that means what you are supposed to, so if you get a corresponding, so basically here in this list, in the lists L1 and L2, obtain I and j such that this relation is maintained. So, note that you can do this in linear time because both the lists are sorted, right. You can find such a common element, and if you do that, then what you are supposed to return, because you have got the value of I and j, is nothing but m of j plus I, and that is the value of the discrete log. Now, let us do an sort of an analysis of this algorithm. First, you know that the steps 2 and 3 can actually be pre-computed, right. So, that means here in this algorithm the steps 2 and 3 can be pre-computed, 2 and 3 can be pre-computed, and if so therefore, if step 6 is successful, that is if alpha power of mj is equal to y is equal to beta alpha power of minus I, then alpha power of mj plus I is equal to beta. So, that means that the logarithm of this value of beta with respect to this value of alpha is nothing but mj plus I. So, this algorithm returning mj plus I is actually correct. So, that gives the correctness of this algorithm. The next is whether this algorithm will terminate. Okay. So, you note that this search is always successful, that is because when you are computing this mj plus I, the maximum value of j is what? M minus 1, and what is the maximum value of I? That is m minus 1. So, when you plug in these maximum values, you get m into m minus 1 plus m minus 1. that is nothing but m minus 1 into m plus 1, that is equal to m square minus 1. So, m square minus 1 is nothing but n minus 1, and I know that the logarithm of beta with respect to b alpha can be maximum equal to n minus 1. So, which means I am checking for all the possible or potential values of the exponent, right, but only this has been done in a slightly clever way. The clever way is because you are essentially using some amount of storage, right, but and you are also doing some amount of time expending some amount of time complexity. But the fun is here that you are actually doing both in terms of order of m, and m is actually square root of n. That means both your time complexity and your space complexity is reduced to order of square root of n, right. So, this is the advantage over the previous two algorithms, right. You are doing a kind of better trade off between the time and the memory requirement of this algorithm, right. So, the algorithm runs in order of m time with order of m memory. Again I am neglecting the logarithmic factors, that is the corresponding log factors are neglected, and this is the complexity, and again note that m is equal to square root of n. So, therefore, this is an order of square root of n time and square root of n time and n memory requirement. Okay. So, now we will actually discuss about another algorithm which is called the Pohlig-Hellman algorithm. Okay. So, this Pohlig-Hellman algorithm is based upon the Chinese remainder theorem. Okay. So, the Chinese remainder theorem, if you remember that we discussed, is basically expressing whole as part, okay, and then using these parts to compute the whole. Okay. So, what you do here is that you take the n, which is the group order, and you decompose that or do a prime factorization of that. Okay. So, therefore, you are believing here that you know the corresponding values like the corresponding prime factorization of n. So, for example, I am assuming here that there are k such prime factors, and you know that by the theory of arithmetic that you know that you can actually obtain like p1 to the power of e1, p2 to the power of e2 and so on, pk to the power of ek, right. So, this is the prime factorization, and all of these prime values are distinct primes, and our objective is again the same, that is we want to compute the logarithm of beta with respect to alpha. So, what is the first objective? The first objective is to, instead of computing a itself, we are trying to compute a, but mod of p1 to the power of pi to the power of ei. That is, we are trying to compute the logarithm, but modulo each of these corresponding p1 to the power of e1, p2 to the power of e2 and so on till pk to the power of ek. Now, once we have them, from there we can actually engage the Chinese remainder theorem and we can obtain the value of a modulo n, right. So, that we know that we have a very efficient algorithm for doing that. So, the main problem is how do I essentially construct the values of a modulo each of these p1 to the power of e1, p2 to the power of e2 and so on, right. And for this we have a very detailed steps. So, let us go gradually through them. Now, suppose you consider that one of those prime factors is q, okay, and the corresponding exponent is c. So, that means you know that if you take modulo q power c, then n becomes congruent to 0 because n is divisible by q power of c. What about q power of c plus 1? It is definitely not 0 because that is the highest value of c is the highest such value, right. You can have at most c factors of q in n, right. So, therefore, n is not congruent to 0 modulo q power c plus 1, right. So, remember that the primes are distinct. Okay. So, we next compute x is equal to a modulo q power c. So, we take a and we want to compute mod of q power c. So, for that we note one thing, that is x, that is this value of x must lie between 0 and q power of c minus 1, right. That means you can always write x like this, right. You can always write them as ai multiplied with qi, where each of these ai's again lies between 0 and q minus 1, right. So, you can always decompose x because x lies between q power of c minus 1. This is you can draw an analogy of this to your normal binomial decomposition, right. You know that if there is a value of x which lies between, say it is less than q power of c minus 1, just replace the q by 2, you will understand the analogy, right. So, therefore, x you can always write as a sigma where I is equal to 0 to c minus 1 ai to the power of qi. Okay. where each of these ai's are actually again lying from 0 to qi minus 1. Okay, and for your I will actually range from, again as is shown in the series, will range from 0 to c minus 1. Now in that case, therefore A, you know that q power of c divides x minus a, right, or a minus x. So that means A is equal to x plus some integer multiplied by q power of c, right. So that is x is this series plus s multiplied with this q power of c, right. So therefore your A is actually equal to sigma of ai q to the power of I, that is the value of when you are ranging I from 0 to c minus 1 plus s into q power of c. So what is this value? This is nothing the value of x, right. So our objective, if you want to find the value of x, we will be to find the values of all these ai's, a0 to a c minus 1, right. So therefore we need to find out, need to determine a0, a1 and so on till a of c minus 1, right. So we need an algorithm through which we can determine from a0 to a c minus 1, right. So the first step is to compute this a0, okay, and for that we give a very nice claim, that is beta and alpha are the two values for which I am needed to find out the discrete log of beta with reference to alpha, and we make a claim, that is beta, the claim is like this, that is if you take beta, okay, and raise it to n by q, then you obtain alpha again raising it to a0 n by q. So that is the claim, okay. So let us see, it is a quite simple proof, that is you know that beta is equal to alpha power of a, right. So therefore your left hand side here is nothing but alpha power of a multiplied or raised to the power of n by q. So what is alpha power of a? Alpha power of a is nothing but sigma of ai qi, q power of I plus s q power of c whole raised to the power of n by q. So now if you just see, that is you have got alpha and just consider a power of 0 here, a power of 0 q power of 0, right, plus a power of 1 q power of 1, that is 1, plus a power of 2, that is again raised to the power of q power of square and so on. The final term is s q power of c, the whole thing is raised to the power of n by q, right. So you note that apart from this term, all the other terms are actually having a value of q in the exponent. So therefore this will be like alpha power of a0 whole power of n by q multiplied with alpha to raised to some constant times n, right. And you remember that n was the order of alpha, so which means that alpha power of n is equal to 1. So that means this is equal to alpha a0 n by q, right. So that actually satisfies this result. So that means if you would like to compute the value of a0, what will you do? You will raise various values of alpha, okay, and say for correspond you will consider like, and you also note one thing, that is the value of a0, you note that it lies between 0 and q minus 1, note this thing, right. So what will you do? You will try with all these q values in the worst case, in a very naive way, you will try for all these q values and you will check that for which case alpha n by to the power of n by q raised to the power of that value of guess, okay, is equal to beta power of n by q. Wherever it matches, you will refer that to as or report that as the value of a0. So what is the time complexity here? It is order of q, right. And if you can actually engage the Shank's algorithm here, then you can reduce it to the order of square root of q, right. So anyway, so basically from order of root q to order of q, you you have an algorithm, you already know a way of doing it, right. So, you can actually obtain the value of A0, right. So, if the value of C that you have got is equal to 1, then it is done, because you do not have any other value of that, any other A values, right. But if your C value is higher than that, then you need to compute A1, A2 and so on till AC minus 1, right. So, this is actually your step 1, which actually computes the value of A0. Okay. So, in step 2 onwards, we will try to compute the other values. Okay. So, for that we have like, so if C is equal to 1, then we are done in the second step, otherwise we proceed to obtain the values of like A1, A2 and so on till AC minus 1. Okay. And for that we actually have got a similar kind of approach, but slightly little involved. Okay. So, what is the claim here? The claim that we make here is this, that is, we say that let us denote this B as equal to beta 0. Okay. We actually engage a recursive technique to obtain the values of A1, A2 and so on. Okay. So, it is a kind of recursive technique. So, first we get A0, from there we obtain a value of beta, and I say that it is beta 1. Okay. So, we start like this, we make so we have obtained A0, right. So, what we do is that after this A0, using this A0 we obtain a value called beta 0. Okay. Now, using this beta 0 and A0 we obtain the value of A1. From A1 we again obtain the value of beta 1. Okay. We gradually continue this until and unless we obtain A of C minus 1, and we stop there. Okay. So, let us see how the definition of beta 1 we can get from the definition of beta 0. Okay. So, your beta 0 or rather beta j is defined like this, beta j is equal to beta, and you raise it alpha to the power of minus A0 plus A1, actually this will be A1q. Okay. So, minus A1q minus A0 plus A1q plus so on till Aj minus 1 Qj minus 1. Okay. So, this beta, so therefore, if you do that, then you get like this, right, beta j is equal to beta, and you raise it to the power of alpha minus A0 plus A1q plus so on, and the final thing is A j minus 1 q of j minus 1. Okay. And you note that beta is nothing but equal to alpha power of A, right. So, alpha power of A minus A0 plus A1q plus so on till A of j minus 1 q of j minus 1, right. Now, what was A? So, if you remember, A was like this, right, A was equal to sigma of Ai q power of I, where I goes from 0 to C minus 1 plus S of q power of C, right. So, therefore, if you plug in this value here, then you get alpha, but you note that all the higher powers remain, but these things are kind of subtracted out from A, right. So, what remains is A power of j, q power of j, right, plus A power of j plus 1, q power of j plus 1 and so on till A of C minus 1, q of C minus 1 plus S of q power of C, right. So, that is your beta j, beta j. Okay. So, what we do next is that we raise beta j like our previous case, like when we computed A0, similar to that, we raise this beta j and we would like to divide it by n by q of j plus 1. Okay. So, if you do that, then you will see that all the higher terms gets cancelled, from this point it gets cancelled except for this one, right. So, here you have got alpha A power of j by q. Okay. But the higher things are again like alpha some other constant k1 again multiplied with n. Again you know that alpha n being a group order, this again goes to unity. So, what you have got is alpha Aj by q, right. So, therefore, again you can actually engage again a Shank's algorithm or a simple algorithm to do a finding for this value of Aj. right. You already know the value of the corresponding beta j, and from there you can engage an algorithm to find the value of aj, right. You know beta j, right, because beta j is your definition. You see that beta j depends upon beta j actually depends upon the coefficient till j minus 1. Okay. So, in your recursive approach, if you have obtained till aj minus 1, then you can actually define the value of beta j, right. So, using this beta j, now you can actually obtain the value of aj, and again using this aj you can define beta j plus 1, right. Again using the beta j plus 1 you can obtain the next value of the corresponding a coefficient, right. So, essentially you can actually summarize these two descriptions like this, that is there are two equations. Okay. One equation is this, that is beta j n by or raised to the power of n by q plus j plus 1 is equal to alpha aj n by q. Okay, I missed an n here actually, there is an n multiplied, right. Right. So, so because of this n, right, so there is an n multiplied. So, therefore, beta j to the power of n by q power of j plus 1 is equal to alpha to the power of aj n by q. This is one equation. The other equation is the definition of beta j plus 1, which you can always define like beta j alpha to the power of minus aj qj. This is the second equation. So, this is exactly the same thing, but only the previous thing has been, I mean you can write that as a recursion like this. Okay. So, what the point is that you can actually engage these two equations and compute the value of a0, then you can obtain the value of a0, then compute the value, compute the next value of beta, okay, and compute the next value of a1, compute the next value of b2, and so on. You can apply them and obtain the value of ac minus 1, repeatedly applying equations 1 and 2, right. So, now we will see some this is a final summarization of that, that is given your g, n, alpha, beta and c and q, you can actually obtain what you are basically doing is computing beta j, raising it to the power of n by q power j plus 1 and checking that for which value it is equal to alpha I n by q. So, whichever value is this, you know that this is the corresponding value of aj, and you are repeating this, right. So, that way you can actually obtain a0 till ac minus 1. So, note that this algorithm is for a particular prime value and for a particular, I mean for a particular prime value and for a particular exponent value. C is the exponent and q is the prime factor and the corresponding exponent. So, you need to repeat this for all the prime factors, right. And what is the complexity of this algorithm? Since you are doing this, and if I assume that each of these step is order of q, and you are doing it for all the c coefficients, the order is like order cq, right. If you use Shank's algorithm, you can actually reduce it to OCQ power of half, right. So, let us consider a very simple and small example like p equal to 29, alpha is equal to 2 and beta is equal to 18, order of n is in this case 28, okay, and therefore, you know that p is the prime value, order is 28 because that is 1 less than the prime value, right. So, that the prime factors are 2 square into 7 power of 1, 4 into 7 is 28, and you set the value of q is equal to 2 and c equal to 2 because that is your first prime value and the first exponent. So, then the step 1a will be like finding the value of a0 because your c is equal to 2. So, that means how many coefficients will you have? You will have a0 and a1, right, and since q is equal to 2, the value of a0 can be either equal to 0 or it can either be equal to 1, right. So, what you do is that you check for this for both these values and you find that in this case, noting that a0 will lie between 0 and 1, in this case we find that when a0 is equal to 1, this equation is satisfied, that is alpha raised to the power of 14 a0 is equal to beta to the power of 14 modulo 29 because that is a modulo p field, right, and your p is 29 here. So, you find that a0 is equal to 1. So, next what you do is that you compute the next value of beta and you raise beta 1 to the power of n by q square and obtain the value of alpha, I mean check when it is equal to alpha to the power of n by q raised to the power of a1. again you do two checks, like because A1 can either be 0 or it can either be 1. So 0 will of course not satisfy this, and you find that 1 satisfies this. You can check that also. So if 1 satisfies, then you know that A0 is 1, A1 is 1. So what is the corresponding value? It is 3, 1, 1, and your prime is 2 here. So it is 3. Okay. So you get that A is equal congruent to 3 modulo 4. So similarly you can do this and find out that A is congruent to 4 modulo 7. So then you can actually apply a Chinese remainder theorem, which we have studied previously, to find the value of A, which is modulo 28, and that is congruent to 11 in this case. So that is your solution, that is the discrete log problem. So here this is the step 1a, and the computation of these things will be the, computation of the subsequent coefficients, the step 1b actually, and you have to do it for all the prime factors. In this case there are two prime factors, one is 2 and the other one is 7, and you obtain the value of the discrete log, right. So this is the basic algorithm for the Pohlig-Hellman algorithm. Okay. So after this we will study the index calculus method and see how much time we have for the next discussions. Okay. So for the index calculus method, the previous algorithms can be applied to any group. Okay. But the present algorithm is more specialized. It finds the discrete log in ZP star, where P is a prime value, okay, and alpha is a primitive element modulo P. So it finds the discrete log in ZP star, where P is a prime and alpha is a primitive element modulo P. So what is done in this index calculus algorithm is by using something which is called a factor base. Okay. So you start with some small primes and assume that your factor base is composed of some small primes, okay, and you, for the first step, there are two steps in this algorithm. Okay. The first step is to compute the discrete log of all these prime values in this factor base. Okay. Suppose the P1, P2 and so on till suppose PB prime numbers are there in your factor base, you compute the logarithm or discrete log of all these prime elements with respect to your alpha, okay, which is the primitive element in ZP star. Then using these logarithms you try to compute the logarithm which is required. Okay. So we will see next how to do that. So the first step is of the algorithm is to find the logarithms of the B primes in the factor base. The second step is to compute the discrete logarithm of a desired element beta using the knowledge of the discrete logs of the element in the factor base. Okay. So let the factor base be equal to P1, P2 and so on till Pb, okay, and assume that C is greater than B, that is C is some number which is greater than P. Okay, it could be like B plus 10 or B plus 20 something in the pre-computation phase. Next what we do is that we actually choose some arbit value of xj, okay, and find out the value of alpha power of xj. It is a random choice, okay, and we factor it out, and the thing is that you have to find out or randomly choose, but check that when you are doing a prime factorization of alpha power of xj, the prime factors should belong to this factor base. That is, it should be expressible in the form of this congruence, that is P1 to the power of A1j, P2 to the power of A2j and so on till Pb to the power of Abj modulo P. Okay. So now if you get such an xj value, and if you so you have to find out j, you have to repeat this and find out C such choices, and note that C is greater than B. Okay. So what we do first is that we can also express this congruence in this logarithm form by taking the log on both sides. Then you have got xj is congruent to A1j multiplied with log of P1 with respect to alpha plus so on till Abj log of Pb base alpha, and note that when you are considering the exponents, then you are doing a modulo of P minus 1, right, because the exponent is modulo P minus 1. So you actually are doing that and you obtain j such, you obtain C such congruences, and since your C is greater than B, you can expect that you will have a unique solution for each of these logarithms. Okay. So using this technique you can try to compute the discrete logs of each of the prime elements in the factor base. That is your first step. Okay. The next step is actually quite trivial. Like what you do is, suppose you already have obtained the discrete logs of the elements in the factor base. We now compute the discrete logs of beta with respect to alpha Now choose a random integer s, where s lies between 1 and p minus 2, and you compute a gamma where gamma is equal to beta multiplied by alpha power of s, okay, modulo p. Now you attempt to factor gamma over the factor base. So therefore again you have to choose s such that gamma can be factored over the factor base, okay, which means you have to repeat this choice of s. Okay. So then if you can factor out, then you have got p1 to the power of c1 and so on till pb to the power of cb modulo p. If you take the logarithm on both sides, then you have got log beta base alpha, which you want, plus s equal to this thing, right. And since you know all these c1s till cb's and you also know all these individual logarithms, computation of this logarithm is actually very simple. You just take this sum, subtract out s and do a modulo p minus 1 operation, right. So therefore this is quite doable, and if there is an example to show that, you take p equal to 1307, alpha is equal to 5, and suppose the factor base here is 2, 3, 5 and 7, okay. The first step is to choose some arbitrary value of x. In this case the choice of x are 4, 0, 6, 3, 5, 1, 3, 6, 9, 8, 6, 5, where if you have raised this alpha to these powers and computed the modulo, you were able to express the outputs in the factor base, okay. So this gives rise to 3 congruences, which if you solve, you will be able to find out the logarithms of each of these primes in the factor base. Then you arbitrarily choose a value of s, in this case a random value of s equal to 7736 gives you the value. If you multiply this with 9451, you will get 8400, which can again be factored in this factor base. If you take a logarithm in both sides and if you subtract out s, okay, right, take the sum and again subtract out s, do a modulo 1306, then you are able to obtain the corresponding logarithm, okay. So I stop here at this point, and just with a note that the complexity of this algorithm is ordered, but it is a sub exponential algorithm, okay, and it actually reduces to order of e1 plus small o of 1 and raised to the power of square root of ln p ln of ln p, okay, which you can prove, but the proof is beyond the scope of this class, okay. So I will just again continue with this discrete log problem in the next class, but a small point which you can think on is this, that is, you can think of this problem like, suppose the logarithm of beta to the base alpha in a group G lies in the interval of s comma t, where s and t are 2 integers, such that 0 is less than equal to s is less than t is less than n, where n is the order of alpha. You can actually think of how will you modify the Shank's algorithm to compute the logarithm of beta to the base alpha in order of square root of t minus s, okay. So you already know the interval and you have to develop the algorithm to do that, okay. So in the next class, my reference has been Stinson's books, and in the next class we will continue with Diffie-Hellman problem.